Yeah, thank you so much for the kind introduction, for your patience with people who fly in too late. And yeah, thanks to all of the organizers for the kind invitation to lecture here this week. Yeah, it's a pleasure to see a highly energetic crowd of the next generation of high energy physics. And also for those who are not in the room at the moment due to COVID reasons, I hope you're doing all right. I hope that it stays a mild one, and hope that I can see you later in the end of the week. Yeah, this is probably the second week of your laser school. I'm really fortunate that last week you had excellent lecturers covering supersymmetry and general relativity. I will try to shamelessly build upon that material and yeah, use it for the purpose of a superstring theory course. I think normally any such course should start with a broad overview what the topic is about. And for string theory, I believe many of the motivations and key selling points are easier to explain once a couple of basics have been introduced. So therefore, I cut it rather short as to the introductory statements on string theory. So just a few things that I can't resist saying. So for instance, string theory is supposed to be a quantum theory of gravity. And it can do so while maintaining manifest contact with low energy notions of quantum field theory and general relativity. So in string theory, you don't jump into the notion of fuzzy spacetime from line one, but instead you can do a lot of warm-up exercises and explicit calculations in a framework that is rather close to both of quantum field theory and general relativity. And I will take advantage of this to show you some features that hopefully make contact with various courses you had before. Yeah, but going far beyond QFT and GR, one of the key selling points of string theory is that it can accommodate gravity while taming its ultraviolet behavior. I think point particle theories of gravity have a horrible reputation for the high energy contributions to their quantum corrections, having to do with certain Feynman integrals that diverge horribly in the UV. And all of these UV issues of quantum gravity get very much smoothed out by strings, having to do with the very basic fact that you have now an extended object which interacts more smoothly and where collisions don't happen at an isolated point in space-time. So with respect to the UV, it's probably a good basis for doing quantum gravity. But yeah, gravity is not the only player in town. We have these gauge interactions and are hungry to see a unification of all interactions in nature. And a first information on why string theory is a good place to do that. Gauge interactions come from open strings. So all of the strong interactions, electroweak sector, electromagnetism, all of that comes from open strings. But by themselves, open strings feel pretty incomplete, and for instance, through their one-loop scattering amplitudes, will shout into your face that they want to be accompanied for closed strings. But closed strings, in turn, is the home of gravity. So no choice in doing gauge interactions alone. String theory will insist that you do gravity along the way, simply because open strings want to have their closed strings along. And some further connections between gauge interactions and gravity that I should mention up front. One of this is the famous ADS-CFT correspondence, on which you will hear a series of lectures, I think starting from Thursday. So I don't need to say much about it. Key idea of ADS-CFT is that a gauge theory, maybe a particularly well-chosen one, is good enough to have all the information about a string theory, which even lives in higher dimension than the gauge theory. This is a super fascinating connection between gauge theory and gravity. And it, in fact, connects the two sides in a strong-weak coupling way, that when one side is weakly coupled, the other side is strongly coupled and vice versa. So this is a, if you wish, non-perturbative duality between gauge theory and gravity, yeah, which literally grew out of string theory. Then yet another neat connection between gauge theory and gravity, which works perturbatively. This is sometimes known as the double copy paradigm. This is about this field theory problem of doing perturbative gravity, of doing some sort of Feynman diagram calculations with gravity. Even if they may have certain UV issues, they are very interesting to study and have implications all the way to gravitational wave experiments. And such Feynman diagram calculations in gravity are notoriously difficult, having to do, for instance, with the fact that the graviton is spin 2 and has 2 Lorentz indices already on polarization tensors of 1 graviton. So it's usually quite a mess if you want to get all the tensor structures correct in gravitational scattering. Yeah, and all of that, both at tree level and at loop level, you can build from gauge theory information. And gauge theory in that sense is way more harmless than gravity, because gauge bosons are just vectors with 1 Lorentz index and not 2. So the combinatorial complexity is so much lower in a gauge theory perturbative setup. And what you can learn from string theory is that there's a kind of squaring relation going on. So the very difficult, if not messy, calculation in perturbative gravity can be assembled from squares of suitably chosen gauge theory building blocks. And, well, if you hear the statement and stare at the respective Lagrangians, then it sounds pretty insane. I mean, like Yang-Mills Lagrangian, like trace F mu nu, it doesn't look like its square will give you the Einstein-Hilbert Lagrangian, namely Ricci scalar. But if you look at the respective amplitudes more from a stringy point of view, if you remember that gauge interactions come from open strings and that gravity comes for closed strings, maybe then it becomes an edge more intuitive. I mean, a closed string you can rip apart and have 2 open strings. And if both of them give you gauge theory in the low energy limit, then why not expect that the closed string that you get from the assembly of 2 open strings gives you some insight about gravity. Yeah, so this is the double copy structure of gravity, which is hard to see within field theory, but which comes almost by definition from string theory. Okay, you can hear that this is also going into the direction of spin-offs. Not only is string theory a candidate theory of quantum gravity, which hopefully describes our universe, but independent on that, string theory is by all means an outstanding tool to learn about new twists in physics and mathematics and everywhere in between. So there are many examples, for instance, how new mathematics was generated by string theory. A very famous example being mirror symmetry, which came up in the 80s. In string theory, you have to be creative about good geometries on which you can compactify space-time, and Calabi-Yau manifolds have good geometric properties which ensure that you can go very low in supersymmetry and get a bit closer to realistic models. Yeah, and these Calabi-Yau manifolds, there are a lot of them, and string theorists came up with new pairings between them, known as mirror symmetry. And this mechanism was completely mind-boggling to mathematicians at that time. There were many of them studying Calabi-Yaus, I mean, before the days of string theory having input on that. And yeah, I mean, it really fell on fertile grounds what string theorists could tell mathematicians working on mirror symmetry. This is just one example of new mathematics coming out of string theory. Another area of mathematics where string amplitudes have a lot to say on, this is number theory, or maybe the intersection with algebraic geometry. Namely, many corners of perturbative string theories are a rich source of special numbers and functions, such as zeta values or their generalizations to multiple zeta values. And in many cases, string theorists could gratefully import some state-of-the-art techniques developed by mathematicians, say motivic, Hopf algebra structures and alike. So there was very intense interaction over the last 20 years on that. But also, string theory could return the favor and tell mathematicians something which wasn't obvious then just to them out of number theory and algebraic geometry. So one prominent example concerns non-holomorphic modular forms, which are produced en masse by closed string scattering amplitudes, and some of them went pretty much outside the scope of how number theorists and algebraic geometers were thinking about modular forms 15 years ago. But okay, I guess I should stop going onto the track of propaganda for my own research directions and rather approach the material that I can pedagogically present in a step-by-step procedure. So let's stop thinking big for the moment and look at the individual pieces of information that I tried to convey this week. Even though the title is Superstring Theory, it will all start with a discussion of bosonic strings. I won't assume any prior exposure to bosonic strings, let alone superstrings, so my apologies to those whom I will bore with this approach. We look at the basics of bosonic strings today, and then there is almost like an intermission tomorrow when we go pretty deep into the rabbit hole of two-dimensional conformal field theory. This is a very rewarding formalism where you can make use of infinite dimensional symmetries and also the full power of complex analysis and theorems on holomorphic functions. I will do this conformal field theory discussion in quite some detail because it will help us a lot to do certain moves in the bosonic string with ease, and it furthermore will help us even more so when we go to the superstring. And in the way I'm doing this, some of the physical nuggets will come comparably late. It may take me all the way to lecture number 3 before you see the graviton emerging. It will take me all the way to lecture 4 or 5 until I can derive the critical dimension for you. So the spoiler is that bosonic strings want to live in 26 spacetime dimensions and superstrings in 10. So all of this will come comparably late because of the chosen approach to make essential use of conformal field theory. If you're getting impatient, don't hesitate to approach me in the break. And I very much hope that what you learn about conformal field theory will be useful to you in various parts of your researcher life. I mean, conformal field theory in 2 dimensions, this is also a big salvation to, say, statistical models or in condensed matter physics. Yeah, conformal field theory will also give us a good approach to string scattering amplitudes. Don't think I will go that deep in the first discussion of bosonic string amplitudes, but I hope I can say more and detailed things in the discussion of superstring amplitudes at the end. Yeah, and when talking about superstring theories, well, first of all, there are several superstring theories on the market, type 1 and type 2, and also heterotic incarnations. I will try to define them at some point in lecture 5 or 6. And perhaps you heard the story that they are all connected by dualities. So please don't get irritated if you hear me talking about 5 superstring theories. It doesn't endanger the uniqueness of the overarching theme of string theories. So I hope that I can say more about this later on. But no matter which of the 5 string theories you look at, you still have several options how to describe them, how to organize the Worldsheet degrees of freedom for them. In the earlier days, there was a distinction between the Green-Schwarz formalism and the Ramon-Neveu-Schwarz formalism, which make use of different worldsheet variables. And then slightly more recently, there was the pure spinor formalism from the year approximately 2000. And if time allows me, I very much hope that I can tell you some basics about the pure spinor formulation of the superstring. But if time is running short and I don't manage to say this, we can first of all discuss in the breaks, and I can also give you some more references, say video lectures and the like. Okay, I hope that's everything I should say up front. Are there any questions about the generalities or the plan of the course? Yes.
Which references do you recommend?
Yeah, okay, I think on the website there are some references which include on the textbook Frontier, the Blumenhagen-Lust-Tyson textbook. Then there are on arXiv very beautiful lecture notes by David Chong from 2009. You will find the arXiv number on the website. I think I also put the link to my lecture notes in the String Theory 1, String Theory 2 course in Uppsala. And oh yeah, since Friday there is another set of lecture notes on the arXiv. Please ask Carlo. Definitely more detailed than the one I referenced in the Uppsala website, so rather look at his than mine. And yeah, I think there are more references on the website that I don't remember at the moment. Any further question? I have a question to you, whether the handwriting is all right. Shall I go bigger, smaller, more colors, less colors? Okay, good. Thank you. Good. Then let's start with chapter number 1. Let's start with basics of closed bosonic strings. No ambition for today to get into chapter 2, 3, or higher than that. I'll only do this. And yeah, let's start with the basic distinction between point particles and strings. And to be more precise, everything is relativistic in this lecture. Already the point particle that I use to compare with a string. Okay, and both point particles and strings, we want to observe how they propagate through space-time. And yeah, here you will see the background dependence on the typical formulation of string theory. I mean, there are also approaches to go beyond the background dependent formulation, but throughout this week, we will study perturbations around Minkowski spacetime. So when I claim that GR is encoded in string theory, you will see this through fluctuations when you have a spacetime metric which is reasonably close to Minkowski, and I will have perturbative statements for you in this perturbation. And yeah, for the metric, we use the mostly plus signature. Then the metric, the determinant is independent on how many dimensions you have. Yeah, and I'm not yet committing to the number of space-time dimensions. Let's keep capital D as a variable, as a parameter, and carry it through the lectures until it will finally get fixed to be 26 or 10 at a later stage. And yeah, it's in this setting where I want to invite you to look at the trajectories smeared out by point particles and strings. So let's start at the point particle side here on the left of the red bar. So a point particle sweeps out a so-called world line in space-time. So I'm really treating space and time on as equal footing as I can while respecting the signature here. And we use a parameter tau called proper time to parameterize this one-dimensional world line. And most of what we will do as a starting point for strings is the generalization of that world line when you're not looking at a point particle, but instead at a string. So what's the stringy analog of that? So in string theory, the basic assumption or premise is that instead of a point particle, you look at some one-dimensional object, a string, and you let the entire string propagate in space-time. So most naively, you can say it's a collection of point particles continuously connected, and each one sweeps out a world line. So you can still use a proper time to describe strings propagating in space-time, but you need yet another coordinate to keep track on where on the closed string you are. So here I'm drawing several snapshots of a closed string, and yeah, connecting all of them will give rise to a two-dimensional surface known as world sheet. And to parameterize, you can augment proper time tau by a periodic spatial coordinate. Let's call that sigma. And here in the closed string case, which I drew on the middle panel, that spatial coordinate sigma is conventionally taken to be between 0 and 2 pi. And the very same exercise can be done for open strings rather than closed strings. So once more, I'm drawing a couple of snapshots of an open string. And each point of that open string smears out its own world line. So by taking the collection of all these world lines, or this continuum generated by them, you once more arrive at a two-dimensional world sheet. But the topology is slightly different. I mean, here, this is topologically like a cylinder, whereas here in the open string case, it looks more like a sail, like you have endpoints, which add a boundary to the world sheet. And the convention for the spatial coordinate in case of the open string world sheet is that this sigma variable, you only dial between 0 and pi. But perhaps this is going in more detail than needed for now. Yeah, and from the viewpoint of this lecture, the CFT machinery is easiest to formulate for closed strings. So it will take me around 3 lectures until I give a formalized discussion of open strings. So if I'm too lazy to distinguish today or tomorrow, you can assume me to talk about closed strings rather than open strings. Okay, now let's see what we can do with these world sheets. And I will give you an action principle for that, which is already the headline for my first section. I will motivate and write down the number go-to action. And what is that about? Well, first of all, let me remind you that point particle physics can be encoded in a world line action. An action functional which gives you the equations of motion for point particles if you vary the action with respect to the fields therein. So in case of point particles, this action functional looks like that. You essentially take the world line length as an action functional. And the length element, the infinitesimal length element for the world line with proper time tau, looks like that. It has a funny square root and bilinears in tau derivatives of the embedding coordinates. Yeah, so there's a shorthand going on here, and throughout the course that dot refers to derivative with respect to proper time. Okay, and the slogan for here is that the motion of point particles goes such that you minimize this action functional, that you minimize the world line length. And one sometimes looks idealistically at an integration range that goes from minus infinity for the proper time to plus infinity. Or let me say the other way around, it's somewhat unnatural in proper time to have cutoffs at finite times. Okay, so this is an action functional which you can vary using field theory methods you probably all know well. And you, like that, can derive the free motion of a point particle. Or if I add some interaction terms like coupling to the electromagnetic field, then I can also derive the Lorentz force like that. And one of the reasons why this is quite aesthetic is, first of all, it is manifestly Lorentz invariant. I'm not singling out x0, so I'm really contracting indices for SO1, D minus 1. And another appealing feature of that action here is that it's independent on the coordinate choice, that you are welcome to reparameterize. You can change your mind about the role of tau. It's invariant under diffeomorphisms on the world line. Maybe it sounds like a bigger word than needed. I think during the entire last week, a diffeomorphism was something you do on the space-time coordinates, you would do on x. But here, I'm thinking about diffeomorphisms on the tau variable. mean, there's just a one-dimensional world line, but nevertheless, I can do general relativity on that world line. And this is not a completely insane comparison, because if you change your mind, replacing tau by some function of tau, let's say a better coordinate might be tau twiddle of tau for some arbitrary monotonic function. Well, then it stays invariant. The transformation of d tau is compensated by the transformation of that square root. And this shouldn't come as a surprise. After all, the length is just a property intrinsic to the world line and not a property of the coordinates I decide to use. Okay, a world line length is intrinsically reparametrization invariant. And the same kind of automatic invariance you get for worldsheet area. So I take this as a motivation for the first action I present for strings. Given that we had so much fun with the world line length in case of point particles, we should, by analogy, try to describe the motion of strings by an action functional that computes the area of these two-dimensional worldsheets drawn up there. So the action principle says that strings want to propagate through space-time in such a way that they minimize the worldsheet area. Okay, how can I write down the worldsheet area in analogy to that one over here? Maybe it is an edge more difficult, or at least it's worthwhile to take an intermediate step. So I should give you a careful derivation of the area element. I mean, here I brutally wrote down what the line element is, but here for the area element, I want to give you a derivation. But before I delve into this, let me just clarify the name once more. The NG subscript stands for Nambu Goto, to whom that action functional is attributed. Okay, how do we compute the infinitesimal area element? Let's look at a piece of worldsheet and pretend that everything is more infinitesimal than I draw it. So once more, proper time is flowing in this direction, and a little piece of worldsheet area I can span using tangent vectors. One tangent vector into tau direction, let's call it dl tau, and then a second tangent vector in sigma direction, let's call that one dl sigma. And maybe you noticed the discrepancy between Lorentz indices and arrows. Indeed, I want to go for a little warm-up in the Euclidean before I give you the final formula tailored to Minkowski spacetime. So let's pretend for a minute or two that we are simply in R to the D, tweaking the signature. And I use this arrow notation whenever I'm taking a breath in the Euclidean. So here, the area element in the Euclidean is meant to be the area of a parallelogram here. A parallelogram spanned by these two tangent vectors, and it's given name to the angle they enclose, theta. And here is a very basic formula, which maybe you have already seen at high school, that for a parallelogram, the area is the two sides spanning it times sine of the enclosed angle. And if you rewrite this in terms of the cosine, or, well, the more accessible expression for the angle is that cosine is essentially the scalar product of the unit vectors. So this, together with a trigonometric formula sine square plus cosine square equal 1, those together give you the formula I'm about to right down here. Okay. And finally, to be clear, these tangent vectors, their explicit form is simply given by the derivatives of x. So that one is, now I'm writing a partial derivative, because there's tau and sigma. And then the other tangent vector is then the partial derivative with respect to sigma. Okay. Yeah, so this is how you assemble the area element in the Euclidean, but this is not quite what we need. In order to transition to the Minkowskian, I just need to put in an extra minus sign inside the square root. And also, I should better roll back to the index notation for SO1, D minus 1 vectors. So then we do this move, x dot. And yeah, I mean, it's so nice to hide the tau and sigma derivatives into dots and other symbols. So for the sigma derivative, I will use a prime. I very much hope that the prime is always distinguishable from a dot. So here is the convention. X prime mu is d sigma. Good. Yeah, so with these prerequisites, I can just write down the final formula now for the area element in the Minkowskian. So not surprisingly, it has a d tau, d sigma up front. And now these Euclidean scalar products simply translate into the following Minkowski dot products. Okay. This is the area element. Let's now assemble everything to the Nambu-Goto action. And I should swamp you with even more notation. It will be convenient here and throughout the course to combine sigma and tau, well, to something which has a similarly neat index notation as x mu. But now I'm going to the beginning of the Greek alphabet to denote a worldsheet index. So alpha, beta, gamma, and their alike will be taken to run over tau and sigma, and therefore have range 0 and 1. And I try my very best to stay in the middle or end of the Greek alphabet when referring to a space-time index like mu, nu, lambda, etc., etc. Okay, and instead of all these d tau, d sigmas, I'll simply write d square sigma, and later on we will go complex and write d square z instead. Okay. Then there is one more abbreviation that we can do. I mean, here, maybe it's not super long, but one can do more compact than that. This content of the square root. Some experts in differential geometry may have already smelled that. You can relate the content of that square root to the so-called induced metric. So what if I start from the metric in space-time, good old Minkowski eta, and now I pull it back onto the worldsheet. So how do I do that pull back? Well, I contract it with a Jacobian of all the dx's by d sigmas. I mean, we should perhaps take a step back to appreciate more. This worldsheet action is a functional for x, which is a map from the worldsheet, sending a pair of tau and sigma into target space, into Minkowski spacetime. And yeah, clearly the worldsheet is embedded in Minkowski spacetime, and it is this Jacobian which implements the pullback of the metric from Minkowski onto the worldsheet. And in principle, pure thought with a bit of differential geometry expertise is already enough to anticipate that the Nambu-Goto action is bound to be the determinant of that induced metric. So strictly speaking, this excursion into the infinitesimal area element wasn't really necessary, but I really wanted to have it as a more gentle derivation and as an excuse to introduce notation on the way. So what I'm writing down here is that the area element derived from that funny parallelogram is in fact the determinant of the induced metric gamma alpha beta. So here a symmetric 2x2 matrix if you wish. Good. So I highlighted about the world line length that this is invariant under changes of the tau coordinates, diffeomorphism on the world line, and of course exactly the same thing goes through for the worldsheet area, now as a two-dimensional analog. The Nambu-Goto action is invariant under worldsheet diffeomorphisms. I keep on using that word. Oops, diffeomorphisms. So once more, this is not the space-time diffeomorphism that you saw in GR all over the place, but this is about diffeomorphisms for the worldsheet coordinates. Suppose you are fed up with the old tau and sigma pair, then you are welcome to pick new coordinates, sigma twiddle, which can be functions of both in tau and sigma. So all kinds of functional dependencies and wild mixings between tau and sigma are allowed, and you won't alter that Nambu-Goto action over there. Yeah, this this is reflecting once more that the area is an intrinsic property of the worldsheet and not a property of the coordinates we decide to use. Then finally, there is an undefined symbol, capital T, since quite a while. So the prefactor T is, can be interpreted as the tension. There is a neat argument by David Tong that if you find a really good coordinate system, then you can show that the T variable here is the ratio of the potential energy divided by the spatial length. And this is the defining property of a tension, say already of an elastic rubber band, the way how its potential energy scales with the spatial length. But a huge difference here is that there is not a Hooke law that energy grows with distance square, but in the string case, energy grows linearly with the string length. That's something we will, for instance, see imprinted in the mass formula later on. But yeah, all this to say, the prefactor has this interpretation as a string length, and I can tell you in the question and answer section what the exact argument of David Tong is and which magical coordinate system manifests that in the best way. There are many competing parameterizations of that tension. I think the most commonly referred to packaging is this. Instead of the tension T, I write 1 over 2 pi alpha prime. And to make the chaos perfect, this alpha prime has units of square meters. So it's the square of something. And if you wish, you can, extract a length scale from it, or you can convert a tension scale into a length scale like that. So the alpha prime variable is sometimes known as the Regge slope. It has to do with how the masses of string excitations correlate with their spin. And the quantity I advertised before was fundamental length scale. Fundamental. L string. Okay, no matter how you twist and turn it, you have the choice between representing the parameter using L string or alpha prime or tension T. And maybe you heard the slogan, string theory just needs one fundamental constant. When people say that, they mean alpha prime. And why people say that is to contrast with the standard model of particle physics, where you need order of magnitude 20 input quantities, such as masses of various quarks and leptons or mixing angles. So everybody in the field agrees that this alpha prime parameter is definitely an input of string theory. And then one can debate on whether one can consider compactifications as additional input data. Of course, alpha prime alone doesn't specify all the solutions of string theory, or for a given alpha prime, there are many solutions to string theory. Those in turn have to do with different space-time geometries, and sooner or later, you can also see a quark mass hopping out of that. But properties of a solution are not as fundamental as a parameter that I'm writing down in the first lecture on a theory. So maybe alpha prime is, at any rate, the most fundamental parameter that you meet inside a string theory. By the way, you don't need a coupling constant. What is sometimes called G Young-Mills in quantum field theory, like a Young-Mills coupling, is the vacuum expectation value of a certain scalar field, the dilaton. So I won't need a separate G string at that stage. This is a dynamically generated quantity, the string coupling. Yeah, at some stages in the course, I will evaluate various quantities as a function of L string, and then it's always instructive to check the L string goes to zero limit, or alpha prime goes to zero. This is a point particle limit, and we will do this to various string amplitudes. And we will see that this recovers quantum field theories, more precisely gauge and gravity interactions at low energies. Strictly speaking, I don't need any limit for alpha prime to find a gauge boson in the open string spectrum, to find a graviton in the closed string spectrum, but they bring along an infinity of extra states. And the extra states, they decouple the smaller and smaller I take L string. Their masses go like 1 over L string. Hence, this limit puts all focus on the surviving gauge gravity states at the massless level. And yeah, as I was already saying a couple of times, gauge theory from open strings, gravity from closed strings. Unless you're in a heterotic theory, maybe I make a footnote on that a little bit later. Yeah, so this finishes what I wanted to say about Nambu-Goto action. In summary, there is an action principle for open and closed strings in Minkowski spacetime on the board. It's here formulated as compact as I could formulate it as a determinant of an induced metric. But if you unpack that, then you still have a nasty square root. A square root with something fourth order in the fields. And you're probably prepared to seeing a quantum theory, a quantization in later lectures. And a square root is never good to quantize. Imagine you do path integrals where the action is in the exponent. Who would ever want to do an integral of an exponential of square root that thing here? This is not going well if we take this action as a final word. So the next step is to give an alternative action where no square root appears, where we don't have that much of an issue of doing in Gaussian integrals in a path integral quantization. So we won't regret it if we spend some time on finding a different action. This is the so-called Polyakov action. For sure, Polyakov was a master in using it, but I think the history of who invented it is more convoluted. So the way how to think about that Polyakov action that I'm about to write down, this is an alternative way of deriving the same field equations. And it's an alternative worldsheet action which bypasses the square root and which has another field along with it, H. This is now a worldsheet metric, and I emphasize this is not the induced metric. I mean, here, that induced metric gamma just came from the Minkowski metric, so more a property of space-time. But now I give the worldsheet the license to bring its own metric. So there is now an a priori independent worldsheet metric. By independent, I mean that it has nothing to do with the above induced metric. And this is denoted by H. The only commonality with gamma is that it has these two free indices, and it's symmetric as a matrix, as every proper metric is. And I will also make frequent use of its matrix inverse. And in absence of better ideas for notation, the matrix inverse is also denoted by H, but now with upstairs indices. All right, here is that Polyakov action, which I claim is classically equivalent to Nambu-Goto. And it is now free of square roots, as promised, and quadratic in the fields. So this is the dream of how an action could depend on the fields. Quadratic, like free Klein-Gordon theory, for instance. Though admittedly the dependence on the metric is a bit more involved. And as I claim, we can eventually get the same equations of motion for x as from Nambu-Goto, but before doing that, let's perhaps first discuss the equations of motion for the metric. And this will hold the key to demonstrating the classical equivalence to Nambu-Goto. Namely, on support of the equation of motion for that new field, the metric, if you impose these equations of motion here, then I will demonstrate in 3 steps that Polyakov action reduces to Nambu-Goto action. And this is what I meant before by classical equivalence. After integrating out the metric, so to say, it gives back the old Nambu-Goto action. Okay, getting there requires, in the way I like to do it, 3 steps. The first one is, well, you will have to compute the variation of this with respect to the metric. So this can take you 3 to 5 lines of computation. And if you shake that variation a little bit, then it will eventually simplify it to the following. This is horrible blackboard management. Okay, I mean, the action is a functional of 2 fields, x and h, and I treat x as constant and do the variation with respect to h. And what I get is a multiple of the following. I get a multiple of, well, not surprisingly, it stays quadratic in x. And now the indices alpha beta of the metric I varied in are either hanging on the derivatives of x or they are hanging on the metric h. Okay, it's proportional to this, and there are a couple of conventional choices. It pays off to not only look at that field variation, but to also normalize it in a certain way. Because this is what's called the energy momentum tensor. Hopefully this is a flashback to the general relativity lecture. Maybe you saw either from Andrea or from Carlo that given an action that depends on the metric, you can extract the energy momentum tensor of the theory through the functional derivative with respect to the metric. Maybe you did an exercise like deriving the Maxwell energy momentum tensor like that. But what I'm referring you to is the energy momentum tensor in space-time. Here, that's a slight paradigm shift. That's the energy momentum tensor on the worldsheet. So we are essentially doing general relativity in 2 dimensions with some metric h, a worldsheet metric h, and this is a completely different story than the target space metric. I mean, I'm using the Minkowski metric to contract the Lorentz indices mu and nu. In case I haven't said that clear enough, whenever you see such a dot product, it's understood to be an index contraction via Minkowski metric in space-time. Okay, so here this is en passant defining the worldsheet energy momentum tensor, and it is essentially the equation of motion with respect to the metric, up to normalization factors. Okay, sorry about all the digressions. What I originally promised was that I give you the variation of the Polyakov action with respect to the metric. It's essentially that. And if you impose that equation of motion, you set the energy momentum tensor to 0. This is step 1, and maybe we do step 2 and step 3 still before the break. Step 2 is to now solve this. I mean, set this to 0 to determine the classical configuration of the metric. So solve it for the metric h and call the solution the classical configuration of the metric. Yeah, I mean, imposing the classical equation of motion, I guess it makes sense to use the word classical in the terminology. And maybe you will now complain that I'm cheating. I will write the classical solution in the following way. As a 2x2 matrix, it's proportional to the induced metric. I'm glad that it's still there. But it's, of course, not quite that. Induced metric won't solve this equation, but there is a scalar multiple, which goes like 2 divided by something with h. And here is the reason that I feel a bit guilty for doing that. I'm promising you a solution for h, but I'm using h on the right-hand side. But don't be scared, this funny factor f will go away in step number 3. So I'm just doing this as a shortcut that we don't spend the rest of the night finishing that calculation. So in this form of the classical metric, we are in good shape to plug that back into the Polyakov action. Plug back, and this f of sigma, this scalar factor, yeah, this is perfect to hide a lot of garbage, and it will drop out as we plug back into the Polyakov action. So we don't need to worry how messy this f is, and in particular, we don't need to worry about the fact that the quantity we want to solve for is somewhere inside that f. Yeah, so imagine you set the metric h in the Polyakov action to this classical configuration. Then there will be induced metrics, and there will also be some f's. But the good thing, all the f dependence occurs in a way that it cancels in between this determinant factor and the inverse metric seen on the right. So I hope here I did the mechanics correctly. I think I was plugging in this into that. And of course, being a 2 by 2 determinant, there is a factor of f squared inside the square root. And the square root ends here. Yeah, so this should manifestly cancel that f factor, so then we can stop worrying what's hidden in there. And what we are left with is some determinant factor of the induced metric gamma. This is already on the right track. And on the right-hand side, I didn't mention a line ago, on the right-hand side we have nothing but gamma alpha beta. The induced metric here represented as a bilinear in X, which contracts its own inverse. I mean, also for gamma, not only for H, I'm just putting the indices of metrics upstairs to refer to the matrix inverse. So all this to say that there is a factor of 2, the range of the alpha beta indices. Okay, so this finishes that calculation I wanted to do in front of your eyes, and we do indeed recover the Nambu-Goto action. Yeah, that's probably a good moment for a 5-minute break. All right, thanks for coming back, and sorry for driving you into an evening shift. I hope you find it rewarding what is happening in the leftover 30 minutes. Now that we obtained this Polyakov action, quadratic in the fields, we are a step closer to having a good starting point to go into the quantum theory of strings. And the next thing we need to settle is what kind of redundancies are in there in this description, or putting it differently, what kind of symmetries does it have? I mean, in case of the world line, I emphasize there is a reparametrization invariance, trading tau for tau twiddle. This is something like a negative degree of freedom. This reparametrization invariance in the world line tells you that the scalar field x mu on the world line doesn't have d degrees of freedom, but only d minus 1. One of them is fake. So it's really important to be on top of things what kind of symmetries are contained in such action functionals. So I will now spell out what the symmetries here in case of Polyakov are, and these symmetries will be crucial to do the accurate degree of freedom counting in the rest of the course. But there's of course also a practical spin-off. Maybe you notice that I'm sneaking around the equation of motion with respect to x. I will give them eventually, but first after using the symmetries in the right way. There's also a pragmatic economic thought behind discussing the symmetries first. Yeah, number one is, I already stressed this property in case of the Nambu-Goto action, and it's the same thing for the Polyakov action. There is once more a diffeomorphism invariance for the worldsheet coordinates. You can once more go wild and reparameterize sigma into sigma twiddle in a way that tau and sigma mix as much as you want. And I already used the buzzword scalar field. I mean, these embedding coordinates, both for the point particle and for the string, these are scalar fields from the viewpoint of the world volume. I mean, the mu index, this is space-time. This is not the vector index on the worldsheet. Hence, every single x mu component is a scalar field on the worldsheet. And under diffeomorphisms, scalar fields transform like that. But let's talk about a quantity which is non-scalar on the worldsheet, namely the metric. It has these two free indices, alpha, beta, and accordingly the metric transforms in the way, as you have learned in GR, how covariant two tensors transform. Contravariant. Yeah, so just grab your GR lectures and look up what a diffeomorphism in space-time will do with a space-time metric. And let's just adapt everything, replacing the word space-time by worldsheet. Yeah. So here is the transformation law for a contravariant 2 tensor. This is how X and H responds to diffeomorphism. And yeah, let me stress, this is a local symmetry, because all these extra Jacobian factors will depend on where in the world we are, depend on sigma or sigma twiddle, no, up to you how to put it. This is symmetry number 1, and to check that it's a symmetry, I just appeal to your GR wisdom. These derivatives transform as covectors. Here you have the inverse metric transforming with the inverse of these Jacobians. So work it out in the way how you worked it out in GR, when you check that something is diffeomorphism invariant. This was symmetry number 1. And number 2 is a so-called Weil transformation. I first write down how a Weil transformation is defined to act on the metric. So I don't assume you to have ever seen such a Weil transformation. View it as a definition. I do this move on the metric, I replace it by itself times a scalar factor, a positive definite one, hence I'm writing omega square rather than omega. And please don't mix it up with a diffeomorphism. I'm not claiming that this is coming from there. Let's instead take it as a definition. A Weil transformation affects the metric as shown, and it leaves, furthermore, by definition, the scalar fields invariant. So this is not a diffeomorphism, but as I indicated through the sigma dependence here, it's also a local symmetry. Okay, and seeing 2 local symmetries, I guess you could all smell that I also show a global symmetry, and this is Poincaré. As a global symmetry of the Polyakov action, you will get away by doing a mix of Lorentz transformation and translation. So this is definition of the Poincaré group, semi-direct product of translation and Lorentz transformations. And of course, lambda as a matrix has to be in SO1, D minus 1. I mean, yeah, lambda is a Lorentz transformation. Yeah, and this is called a global symmetry because you should better choose them to be independent on sigma. I mean, the only situation where you make them sigma dependent is when you derive the Noether currents, but then it's not a symmetry. I mean, the Polyakov action is only invariant under global such Poincaré transformations. Yeah, and these symmetries will be extremely important to us, in particular that Weil transformation. Maybe I can say it right away that we would be drowning in negative norm states if it wasn't for the Weil symmetry. And for that reason, whatever we do, we have to keep these symmetries alive by all means. And that in turn means, if you adhere to those symmetries, there is a lot of stuff that you cannot do. So it's in particular the Weil invariance which rules out a lot of extra terms that you could be tempted to add to the action. I guess from QFT you are trained to think about creative extra terms that you can add to the action. I mean, a free Klein-Gordon scalar wants to have a phi cube or phi to the 4th interaction. And maybe a similar association with Einstein gravity that you want to give it a cosmological constant. But both of these moves are taboo if you want to have Weil symmetry. So as an analog of this phi to the 4th extension of Klein-Gordon scalars, you could imagine to add a potential term to the Polyakov action. Or you could, to stay in the cosmological constant picture, you could contemplate an addition like that. And both of them are okay with the diffeomorphism invariance, but they both break the Weil invariance. So even though I haven't given you the justification why these are holy, let me state right here that we will refrain from considering such extra terms on behalf of the Weyl invariance. Okay, so by V I mean an arbitrary Lorentz invariant function of x, a potential term which may or may not be polynomial, but no matter how you choose the polynomial, the metric transforms with omega, but we are not having the inverse metric which was saving the day in the Polyakov action. I mean, it is the interplay between this and that which is responsible for the Weyl invariance. And you can furthermore see that 2 dimensions are crucial. I mean, this determinant would have a different scaling if it was in 3 or higher dimensions. So it's a quite magical tuning to be in 2 dimensions, to have this possibility of Weyl invariance. Yeah, it's for all of those reasons that we are not adding or considering such extra terms for S Polyakov. Okay, with all of these motivating remarks for the uniqueness of Polyakov action, let's go and solve some equations of motion. I want to resolve the cliffhanger about equations of motion for x, and I want to show some classical degrees of freedom in the solutions for x, and I furthermore want to give a first overview of the kind of constraints that we will encounter from the energy momentum tensor on the worldsheet, which has to vanish. Okay, we want to do all of this in a gauge-fixed way, where we make use of these Polyakov symmetries. There is a total of 2 + 1 local symmetry degrees of freedom. Namely, the diffeomorphism comes in 2 components, sigma twiddle 1, sigma twiddle 0. And there's a third degree of freedom for the Weyl transformation. So this is the number of local symmetry degrees of freedom. And if you count carefully, this is the same number of degrees of freedom that we have in the metric. This is a convenient matching. The metric comes across as a symmetric to index tensor. Alpha, beta take range 0, 1. So symmetric 2 by 2 matrix has 3 independent entries, which matches the degrees of freedom in the symmetry transformation. So it looks very good that we can as if we can completely eliminate the metric. And well, in some sense it's true, but only locally. This is a magic word that I will use 1,000 times, and I'll try my best to explain it already here. So why can't we eliminate the metric globally? Let's see how this elimination procedure works in practice. Let's go into a very nice gauge where the metric has very little non-trivial entries. For instance, a very simple configuration could be that as a 2 by 2 matrix, the worldsheet metric could be Minkowski, but now a 2-dimensional Minkowski. I mean, the ultimate dream is to get the worldsheet metric into this form. And as a slightly more modest step, I want to make it a multiple of eta. And I can try to do that by means of this transformation law for h twiddle upstairs. So it's enough to have these 2 degrees of freedom in the diffeomorphisms. So here I'm highlighting why it's 2. Namely, there is this alpha index in the old or new coordinate sigma or sigma twiddle. You have 2 jokers to cook up your favorite sigma twiddle to enforce that the metric goes into this form. I mean, just imagine it's not the case. Just imagine you have a horrible metric H. But then you can try to find a good sigma twiddle, which does you the favor that the transformed metric is proportional to eta. So this is a differential equation for sigma twiddle 0 and sigma twiddle 1. It's coupled partial differential equations to get here. So these coupled PDEs on the desired diffeomorphism that does the job, well, you can ask your mathematician friends whether there exists a solution or not, and what will a mathematician say? Yeah, there are local existence theorems. As always, when you deal with non-standard differential equations, a theory of solutions usually starts with a disclaimer, this holds locally. And that's exactly the case for the desired sigma twiddle to arrive at this conformal gauge. That's why I'm cautious and say that only locally you can trivialize the worldsheet metric. And the concrete consequence of not having that globally, this becomes important when we take worldsheets of non-trivial topology, and there will be several remarks on that towards the end of the course. But yeah, let's for the moment be happy with locally being in this Minkowski form. And let's in particular look at the simplified version of the Polyakov action, if we pick this conformal gauge. So I'm referring to this choice of the metric over here. It simplifies the Polyakov action too. And in fact, it's enough to be proportional to eta, essentially by Weil invariance. This omega square factor is not disturbing us in the same way as this f factor from before the break was dropping out. So the omega dependence coming from the square root determinant is killed by the omega dependence on the inverse metric. And once the dust settles, we just have this Minkowski metric on the worldsheet contracting the derivatives with respect to tau and sigma. And there's furthermore the Minkowski metric in spacetime contracting the axis. So I hope I'm not confusing you by using a C dot for the spacetime index contraction, whereas the worldsheet indices are all written out. Okay, so this is the simplified version of the Polyakov action. Let me give it its own acronym, CG, for conformal gauge. And this is the right formulation where it's fun to take the equation of motion with respect to x. We could have done it for general H, then you would have seen a relativistic wave equation, but in view of the limited time we have here, let me make sure that you are getting served the equation of motion for x in the most useful way, which is in conformal gauge. So this is now that the dynamical degree of freedom of H are manifestly gone. This is a free wave equation in two-dimensional Minkowski spacetime. So the field variation with respect to x is simply proportional to this wave operator. Keep in mind that we have a signature -1 comma +1, so this is minus del tau square plus del sigma square. And this is the classical equation of motion for x that we will solve in a minute, and which will be our first estimate of what kind of worldsheet degrees of freedom there are to describe the string and its spectrum and later its interactions. Yeah, I wanted to be honest that conformal gauge is enough in the sense that you can carry around the omega and nothing really breaks. So going to a multiple of eta is already good enough, but just in case you find it disturbing to see the free-floating omega square factor, you can of course still use the Weil invariance to completely trivialize the worldsheet metric. So if you want to, you can further enforce that this omega square factor in conformal gauge is set to 1, and you can locally insist that H is literally eta without a proportionality factor. But this is just a side remark. Whenever I refer to conformal gauge, henceforth, I mean this one, and it will be good enough for most of our purposes. Okay, let's play a bit more with the free wave equation that was coming out of the conformal gauge Polyakov action. And let's now study its classical degrees of freedom. Or in other words, let's do a Fourier expansion or mode expansion, as one often says. Yeah, what's the best strategy to solve this two-dimensional wave equation? There's something neat about the wave operator in 2 dimensions, which is no longer there in higher dimensions. Namely, the wave operator factorizes. And to make it factorize, let's pick the light cone coordinates on the worldsheet, which are sigma plus minus, which are just these simple combinations, tau plus sigma or tau minus sigma, respectively. And needless to say, the associated derivatives with respect to sigma plus, sigma minus are equally simple combinations of del tau and del sigma. Don't forget the factor of a half if you solve a homework problem on this. Yeah, and in these light cone coordinates, that wave operator, as promised, takes this factorized form, maybe with a funky factor of 4. Yep. Okay, why is it nice to have this factorized form? Now, it's very easy to describe a general solution to it. Okay, maybe I need to squeeze a little bit. How to solve this wave equation with a conveniently factorized operator? Well, any function which only depends on sigma plus but not on sigma minus will be annihilated by the wave operator. So no matter what the functional dependence of this XL is on sigma plus, it will always be a solution to that. And likewise, an arbitrary function of one variable sigma minus only, this is yet another independent solution, and needless to say, their sum is a solution as well. Okay, this is a solution to the differential equation, but usually differential equations come combined with some initial condition, boundary value, etc., etc. And here, the boundary condition is that we are describing closed strings. So we are only accepting a solution that respects this periodicity of the spatial parameter of the closed string worldsheet. So we have to be pretty careful which functions XL and XR we pick. Our choice needs to respect this periodicity. So I was lying before, you can't take a random function of x plus and x minus. You must choose the functions wisely, such as this periodicity is not violated. Okay, as you see, I'm bailing out from squeezing it on the bottom of the upper blackboard. What is now an expansion of these individual solutions that preserve the periodicity? Okay, well, if you think in terms of Fourier series, you just need to make sure that you are doing a Fourier expansion in sigma plus. Periodicity in sigma also means let's please have a periodicity for sigma plus. So to zeroth approximation, it will do the job to combine a Fourier zero mode with an infinite sum over plane waves. So here is a possible way to parameterize all of these plane waves. Here they are, e to the minus in sigma plus, all of them individually periodic. And you can do the same thing for sigma minus. So both x left and xr will definitely have this Fourier series. And I admit that at first glance, this notation may look very opaque. So all these prefactors and all the different alphas here are for later convenience. So my apologies, it's really a historic thing that this inverse string tension is denoted by alpha prime, and this is a very different alpha than the Fourier coefficients here and there. So it's a mixture of historic artifacts, and the normalization factors there are for later convenience. So if I just promise you Fourier expansion, maybe you would have imagined something slightly slimmer, but please bear with me, this notation will pay off eventually. Invariance. Yeah. Okay, so these are all the Fourier non-zero modes. What about the Fourier zero mode? So here, let's do the following. Let's write down a term which naively violates the periodicity. So here is a naked sigma plus, which by itself is not periodic, but we can compensate for that. Namely, if we give the XR accompanying term sigma minus with the same vector coefficient p mu, then everything is fine. Then in combination, it is compatible with the aspired periodicity. So this adds up to something you know really well. If you add up those two terms, then what you find is it looks like just the free motion of a point particle on a straight line. So this clarifies what the interpretation is of the zero mode sector. There's a center of mass position little x mu for the string, and then these coefficients of sigma plus, sigma minus, they are to be interpreted as space-time momentum, or a kind of velocity. Yeah. And I have completely missed to explain the names. One writes x left for left movers. I mean, just think back in high school days when you were describing wave propagation. If you have a function of sigma plus tau, and make different snapshots at tau, tau plus 1, tau plus 2, then various ripples of waves will walk to the left as you follow in time. And similarly, we say right mover for random functions of sigma minus. Well, same story. If you put snapshots at tau, tau plus 1, tau plus 2, then whatever excitation you put, it walks to the right. And yeah, we somehow split now all these excitations that solve the wave equations into oscillators, Fourier non-zero modes. And here is a Fourier zero mode sector, which is just like a point particle. So one can roughly say that here is where all the string effects are sitting, and from the perspective of the zero mode, it rather resembles the point particle. Okay, these are the classical degrees of freedom, or this is maybe an upper bound to the classical degrees of freedom. We still haven't imposed the equations of motion for the metric. So let's see what is left of these degrees of freedom, or what kind of conditions we need to impose. So I'm still writing classical, since all we do for today is solving equations of motion. So we still have to impose that the variation with respect to the metric vanishes, and I hope that nobody is getting confused with the trivialization of the metric. Well, we did say that we want to have eventually a worldsheet metric in conformal gauge. But the equations of motion with respect to h has to be taken before. So you can, of course, use this tweak after taking the equation of motion, but the two of them don't commute. So the slogan is first vary and then go to your favorite gauge. Yeah, we still have to impose that. And yeah, we already introduced a nickname for the thing that has to vanish on the support of these classical equations of motion. It's the energy momentum tensor on the worldsheet, now in conformal gauge. So remember, it was defined with this convention-dependent factor. It is exactly in this normalization that I will use it throughout the course. And as I keep on saying, first vary, and then once you are done with this field variation, then plug in conformal gauge condition. And well, it's almost identical to the expression you've seen before. Maybe you already noticed back then that the energy momentum tensor depends very mildly on the metric h, and accordingly the simplifications in conformal gauge are not that earth-shattering. It is what it is, and here it is written out. Yeah, this is a quantity that has to vanish for each value of the indices alpha, beta. So it seems like there is a 2 tensor worth of equations. But let's count carefully. How many of these equations are really independent? It looks like we have a symmetric tensor. So this kills an antisymmetric component. But furthermore, compute its trace. If you contract it with eta alpha beta, then here this downstairs eta becomes a 2. So with this fine-tuned factor of -0.5, the trace vanishes. So what we are dealing with is a traceless symmetric 2x2 tensor, and this has 2 independent components. So there are 2 independent constraints only, not 3 of them. As you will see tomorrow, having a traceless energy momentum tensor is a hallmark of so-called conformal symmetry. This is true not only in 2 dimensions, but in any number of dimensions. And yeah, here for us, it means that, well, we can fish out our favorite linear combinations. We can fish out 2 linear combinations of T alpha beta components that we need to set to 0. I would recommend those because taking these linear combinations simplify the component to that. Either it's the Minkowski square of del plus of x, or it's the Minkowski square of del minus of x. So these are the things that have to vanish. And I'm a bit reluctant to put light cone indices on the T, but if you are okay doing that, the tracelessness translates into T plus minus being 0. Yeah, it's always a bit cumbersome to go from Cartesian into light cone coordinates, but if you feel as of doing that, tracelessness looks like that, and then those are simply T plus plus and T minus minus, the leftover components, when you know that it's symmetric and traceless. Yeah, so apparently we should pay more attention to the partial axis in order to track the classical constraints. So good news about these derivatives. They have a simplified mode expansion. In particular, we can do some notational cosmetics if we are introducing the missing alpha 0. So let me introduce that. You saw alpha with non-zero subscript. But now I'm introducing yet another one, which is just this p mu, this vector in the mode expansion along with the linear piece, sigma plus, sigma minus. And here there is no difference between the twiddled and the untwiddled incarnation. Okay, so there is a shared 0 mode to del plus of x and del minus of x, independently for each value of the Lorentz index mu. And now we can really write down a clean sum over all integers, little n. Oh yeah, sorry if I haven't emphasized that. I only said what n is not equal to, but I missed to point out that n is actually running over integers, positive and negative ones. All of them except for 0. Yeah, and this gap is now getting filled with this definition of alpha 0. And yeah, here they are, the Fourier expansions of these two vectors whose Minkowski norm ought to vanish. Yeah, so having a neat Fourier expansion for the partial axis, we can also look at the constraint equation in a Fourier expansion. So for T alpha beta, let's do the same type of Fourier expansion. And then each Fourier mode of T plus plus and T minus minus has to vanish separately. So let's get those on the board and look at a small corollary on the mass spectrum, and then we are done for today. Yeah, as I was saying, let's look at the Fourier modes of these vanishing squares. And classically, they have to vanish dead on. I emphasize that this is with a disclaimer of classically. There will be something like a 0-point energy that we have to consider in the quantum theory. But let's shift the discussion of these quantum effects for tomorrow. So for now, we classically impose that the following Fourier coefficients vanish. So here I'm getting ahead of myself. These capital L's, these are the definitions of the Fourier modes of the energy momentum tensor, namely L without a twiddle for T plus plus, and an L twiddle for the other one, T minus minus. Yeah, I hope that there is a kind of rhyme to this notation, that everything associated with to the right mover tends to get a twiddle. Both the alphas and the L's, and maybe some other quantities such as BC ghosts in later lectures. Yeah, so this is coming from T plus plus, and that is coming from T minus minus. Okay, so for each integer, there is a Fourier coefficient L and L twiddle that we have to zero. And the Fourier zero mode, n equals 0, is particularly noteworthy. Namely, this gives you some information about the mass spectrum. This is where you can get the so-called mass shell condition from. Yeah, so my apologies for that jargon. Mass shell refers to having a fixed Minkowski norm for the spacetime momentum p. So p square is with a mostly plus signature, the negative mass square. And L0 will contain that p square. I mean, remember, we defined an alpha 0 to be that momentum vector that we saw in the linear piece of the mode expansion. So if we want to have information on p square, we should look at the right choice of L, which has an alpha 0 times alpha 0. So clearly, that luxury only arises by poking at the L0 constraint. And yeah, the L0 constraint gives you an exact expression for that m square, or for the value of minus p square. Namely, it's some infinite linear combination of the alphas, namely these Fourier non-zero modes. And it's quite funny, we have separately an L0 and an L0 twiddle, and both of them contain p square. Because as I was just saying, p square is a shared zero mode for alpha 0 and alpha 0 twiddle. So the very same mass formula arises if I switch from untwiddled alphas to the twiddled ones. Okay, so this will be the blueprint of how the string effects encoded in the Fourier non-zero modes, how they give rise to a very interesting mass spectrum. So far, these are classical Fourier coefficients, but in a quantum discussion, they become operators. Or we will study the conformal field theory analog of tentative operators. So the spoiler to end this lecture, or as an appetizer for tomorrow, this will turn into a quantum statement for masses of Hilbert space states. And there will, among other things, be an integer shift to that. Or more precisely, the quantum effect being that the m squares will still have an overall form over alpha prime, but then there is a -1 as a quantum effect, and then some operator-valued version of alphas or alpha twiddles. And part of that spoiler is that it's actually two equations that you can always exchange the alphas for the alpha twiddles. That's a condition known as level matching, which morally says that the left and right moving degrees of freedom of the closed string, that they have the same contribution to the m squares, or that the left movers predict the same mass square as the right movers do. But okay, I think it's time to wrap up now. This was the classical discussion of closed bosonic strings, a worldsheet action principle with some very interesting symmetries, combination of diffeomorphism and Weil invariance. And tomorrow I will try to discuss in all detail what you can do with such symmetries in 2 dimensions and how to take maximal advantage of their infinite dimensional nature. Good, thank you.